Hello everyone. Myself Mr. S.M. Ghanwat working as Assistant Professor in Mechanical Department at Sharad Institute of Technology College of Engineering Yadrao Ichalkaranji. We are discussing unit number 3 equilibrium diagrams. In this session of part 8 we are going to discuss continuous cooling transformation diagrams. Also we are going to take review of phase transformation and mechanical properties for iron carbon alloys. Now we are going to discuss continuous cooling transformation diagrams. Isothermal heat treatments are not the most practical to conduct because an alloy must be rapidly cooled to and maintained at an elevated temperature from a higher temperature above the eutectoid. Most heat treatments for steels involve the continuous cooling of a specimen to room temperature. An isothermal transformation diagram is valid only for conditions of constant temperature. This diagram must be modified for transformation that occur as the temperature is constantly changing. For continuous cooling, the time required for a reaction to begin and end is delayed. Thus, the isothermal curves are shifted to longer times and lower temperatures as indicated in figure. For an iron-carbon alloy of eutectide composition, a plot containing such modified beginning and ending reaction curves is termed as continuous cooling transformation diagram, or we call it as CCT diagram. Some control may be maintained over the rate of temperature change depending on the cooling environment. Two cooling curves corresponding to moderately fast and slow rates are superimposed and labeled, again for eutectoid steels. Once again, we will just go through the concept of CCT diagram. Isothermal heat treatment are not the most practical to conduct because an alloy must be rapidly cooled to and maintained at an elevated temperature from a higher temperature above the eutectoid. Isothermal heat treatments are not the most practical to conduct because an alloy must be rapidly cooled to and maintained at elevated temperature from a higher temperature above the eutectoid. Most heat treatments for steels involve the continuous cooling of a specimen to room temperature. An isothermal transformation diagram is valid only for conditions of constant temperature. This diagram must be modified for transformation that occur as the temperature is constantly changing. For continuous cooling, the time required for a reaction to begin and end is delayed. Thus, the isothermal curves are shifted to longer times and lower temperatures as indicated in figure. For an iron-carbon alloy of eutectide composition, a plot containing such modified beginning and ending reaction curves is termed as continuous cooling transformation diagram. Some control may be maintained over the rate of temperature change depending on the cooling environment. This is all about the continuous cooling transformation diagram. Now we are going to discuss moderately rapid and slow cooling curves superimposed on a continuous cooling transformation diagram for a eutected iron carbon alloy. Also, we are going to discuss continuous cooling transformation diagram for a eutected iron carbon alloy and superimposed cooling curves, demonstrating the dependence of the final microstructure on the transformation that occur during the cooling. Now, let's start with this particular point. two cooling curves corresponding to moderately fast and slow rates are superimposed and labeled in figure. Again, for a eutectoid steel, the transformation starts after a time period corresponding to the intersection of cooling curve with the beginning reaction curve and concludes upon crossing the completion transformation curve. The microstructural product for the moderately rapid and slow cooling rate curves are shown in figure and are fine and coarse perlite respectively. Normally, bainite will not form when an alloy of eutectoid composition or for that matter any plain carbon steel is continuously cooled to room temperature. This is because all of austenite has transformed into perlite by the time the bainite transformation has become possible. Thus, the region representing the austenite-perlite transformation terminates just below the nose, as indicated by the curve AB. For any cooling curve passing through AB in figure, the transformation ceases at the point of intersection with continued cooling. The unreacted austenite begins transforming into martensite upon crossing the M-start line. With regard to representation of the martensitic transformation, the M-start, M50% and M90% lines occur at identical temperatures for both isothermal and continuous cooling transformation diagram. This may be verified for an iron-carbon alloy of eutectoid composition by comparison of figures. For the continuous cooling of a steel alloy, there exists a critical quenching rate, which represents the minimum rate of quenching that produces a totally martensitic structure. This critical cooling rate, when included on the continuous transformation diagram, just matches the nose at which the perlite transformation begins, as illustrated in figure, as the figure also shows only martensite exists for quenching rates greater than the critical one. In addition, there is a range of rates over which both perlite and martensite are produced. Finally, a totally perlitic structure develops for low cooling rates. Carbon and other alloying elements also shift the perlite, as well as pro-eutectide phase, and bainite noses to longer times, thus decreasing the critical cooling rate. In fact, one of the reasons for alloying steel is to facilitate the formation of martensite so that totally martensitic structure can develop in relatively thick cross section. The figure is going to show you the continuous cooling transformation diagram for the same alloy steel for which the isothermal transformation diagram is represented. The presence of bainite nose account for the possibility of formation of bainite for a continuous cooling heat treatment. Several cooling curves superimposed on the figure indicate the critical cooling rate and also how the transformation behavior and final microstructure are influenced by the rate of cooling. Of interest, the critical cooling rate is decreased even by the presence of carbon. In fact, iron-carbon alloys containing less than about 0.25 weight% carbon are not normally heat-treated to form martensite because quenching rates too rapid to be practical are required. Other alloying elements that are particularly effective in rendering steels heat-treatable are chromium, nickel, molybdenum, manganese, silicon, and tungsten. However, these elements must be in solid solution with the austenite at the time of quenching. In summary, Isothermal and continuous cooling transformation diagrams are, in a sense, phase diagrams in which the parameter of time is introduced. Each is experimentally determined for an alloy of specified composition, the variables being temperature and time. These diagrams allow prediction of the microstructure after some time period for constant temperature and continuous cooling heat treatment respectively. Now we are going to discuss review of phase transformation and mechanical properties for iron carbon alloys. The figure is going to show you the possible transformations involving the decomposition of austenite. Austenite is decomposed, or decomposition of austenite is done in perlite plus pro-eutectide phase, second bainite, third martensite, and then after reheating it is converted to tempered martensite. Then after slow cooling with diffusion transformation, we will get the perlite and prototype phase. After moderate cooling, we will get the bainite, austenite to bainite transformation. And for diffusionless transformation, we will get the martensite with rapid quench. Transformation of austenite with slow cooling will get the perlite as the transformation product. Austenite with moderate cooling we will get bainite as the transformation product, which involves diffusion, and in diffusionless transformation with rapid quench we will get martensite and tempered martensite as the transformation product of austenite. Now we are going to discuss the mechanical properties associated with the iron carbon alloys. We now discuss the mechanical behavior of iron carbon alloys having the microstructure discussed herefore, namely fine and coarse perlite, sphaerotite, bainite, and martensite. For all but martensite, two phases are present, ferrite and cementite, and so an opportunity is provided to explore several mechanical property microstructure relationships that exist for these alloys. We will start with the perlite. Cementite is much harder but more brittle than ferrite, thus increasing the fraction of Fe3C in a steel alloy while holding other microstructural elements constant will result in a harder and stronger material. We can demonstrate it with the help of a tensile and yield strength and the Binel hardness number we are plotted as a function of weight percent carbon for steel that are composed of fine perlite. All three parameters increase with increasing carbon concentration. In as much as cementite is more brittle, increasing its content result in a decrease in both ductility and toughness or impact energy. These effects are also for the same fine perlitic steels. The layer thickness of each of the ferrite and cementite phases in the microstructure also influences the mechanical behavior of the material. Fine perlite is harder and stronger than coarse perlite, as demonstrated. The reason for this behavior relate to a phenomena that occur at alpha Fe3 phase boundaries. First, there is a large degree of adherence between the two phases across a boundary. Therefore, the strong and rigid cementite phase severely restricts deformation of the softer ferrite phase in the regions adjacent to the boundary. Thus, the cementite may be said to reinforce the ferrite. The degree of this reinforcement is substantially higher in fine perlite because of the greater phase boundary area per unit volume of material. In addition, phase boundaries serve as a barrier to dislocation motion in much the same way as grain boundaries. For fine perlite, there are more boundaries through which a dislocation must pass during plastic deformation. Thus, the greater reinforcement and restriction of dislocation motion in fine perlite account for its greater hardness and strength. Coarse perlite is more ductile than fine perlite, which plots percentage reduction in area versus carbon concentration for both microstructure types. This behavior results from the greater restriction to plastic deformation of fine perlite. This is all about the perlite. Now we are going to discuss the spheroid. Other elements of the microstructure relate to the shape and distribution of the phase. In this respect, the cemented phase has distinctly different shapes and arrangements in the perlite and spheroid microstructures. Alloys containing perlitic microstructures have greater strength and hardness than do those with spheroid. We can demonstrate it with and compares the hardness as a function of the weight percent carbon for spheroid with both the perlite structure types. This behavior is again explained in terms of reinforcement at and impedance to dislocation motion across the ferrite cemented boundaries as discussed. There is less boundary area per unit volume in spheroid and consequently plastic deformation is not nearly as constrained, which gives rise to relatively soft and weak material. In fact, of all steels alloys, those are that are softest and weakest have a spheroid microstructure. Now we will move further with the next, that is benite. Because benedict steels have a finer structure, they are generally stronger and harder than perlitic steels, yet they exhibit a desirable combination of strength and ductility. Now, temperature ranges over which perlite and benite forms consistent with the isothermal transformation diagram for these alloys and are noted at the tops. Now we will move further with the next phase, that is martensite, or next point, that is martensite. We are discussing mechanical properties associated with iron carbon alloys. Martensite of the various microstructures that may be produced for a given steel alloy. Martensite is the hardest and strongest and in addition the most brittle. It has in fact negligible ductility. Its hardness is dependent on the carbon content, up to about 0.6 weight percent as demonstrated, which plots the hardness of martensite and fine perlite as a function of weight percent carbon. In contrast to perlitic steels, the strength and hardness of martensite are not thought to be related to microstructure. Rather, these properties are attributed to the effectiveness of the interstitial carbon atoms in hindering dislocation motion and to the relatively few slip systems for the BCT structure. Austenite is slightly denser than martensite and therefore during the phase transformation upon quenching, there is a net volume increase. Consequently, relatively large pieces that are rapidly quenched may crack as a result of internal stresses. This becomes a problem especially when the carbon content is greater than about 0.5 weight percent. Now we are going to see the reference part. For this session, the reference is William D. Callister Jr., David G. Rathwich, Material Science and Engineering, an Introduction. For further reading, you can refer this particular reference book for Introduction to Material Science and Engineering. Thank you.